Empezamos. Dale. ¿Y 12:30 terminamos? Ok. Okay, we will start where I left yesterday. I was presenting the hawks and doves game, and we saw that if C, that was the pay due to the fighting, was higher than Chi, that was the reward. So neither the hawk nor the dove, this is okay. The dove, this should be a D, is evolutionarily stable. So the idea is that with this matrix, we couldn't find a Nash equilibrium between these pure strategies. So dove and hawks were not a Nash equilibrium. So we need to find a Nash equilibrium among the mixed populations, the mixed strategies. So what we are going to do is to propose a strategy, a mixed strategy with this shape. So with a probability rho of playing hawk and a probability 1 minus rho of playing dove. This is the strategy that I am proposing to be the Nash equilibrium. And the idea is to find which is the value of rho. Okay? So for that, suppose that now I am confronting, let's call this the strategy P. So suppose that now I am trying to find the payoff of a hawk while fighting with P or playing with P, and the payoff of D while again competing with P. So I want these two payoffs to be calculated. And this is what I am doing here. So if I am choosing a hawk as a strategy and I am competing against this strategy, the payoff for H would be rho multiplied by the payoff of a hawk competing with a hawk, plus 1 minus rho times the payoff of the hawk competing with a dove, because this strategy has a fraction of rho, or a fraction rho of playing hawk, and a fraction 1 minus rho of playing dove. So the payoff of a hawk against P should be calculated in this way. And when we do these calculations, what we find is that the payoff for a hawk competing with this new strategy has this value. And now, suppose that I am choosing dove, and again, I want to calculate the payoff of a dove while competing with this strategy. And the payoff is this one. So it's rho times the payoff of a dove competing with a hawk, plus 1 minus rho times the payoff of a dove competing with a dove. And this is the expression for the payoff of a dove competing with the strategy P. So if I want neither the hawk or the dove to take advantage when competing against this new strategy, because if this is a Nash equilibrium and it's a mixed strategy, if the hawk gets some advantage while competing as a hawk, so instead of choosing this strategy with a given fraction rho of hawk and a given fraction 1 minus rho of dove, if the hawk is taking advantage, I will increase my fraction of hawk, because it is much better to play as a hawk. Or if the dove is taking advantage, and I have already chosen this strategy, rho and 1 minus rho, as my mixed strategy, if dove is taking advantage, I will try to move to dove and increase my fraction of dove. So if I am in a Nash equilibrium, the condition to be in a Nash equilibrium is that neither a hawk nor the dove can take advantage while competing with this strategy. So for that, what I need to ask for is that this payoff be equal to this payoff. So the payoff of the hawk while competing with this strategy should be equal to the payoff of the dove while competing with this strategy. So I need this expression here to be equal to this expression here. And that leads to the condition that rho should be equal to Chi over C. Okay? So I have already, so by that, by doing that, I have found a fraction of hawk and a fraction of dove that give place to a mixed strategy, and this mixed strategy is actually a Nash equilibrium. So I have found the Nash equilibrium for this game, and the Nash equilibrium is the following, is G over C times playing as a hawk, and 1 minus G over C times playing as a dove. So this is the Nash equilibrium of this game. Okay, and again, I have told you yesterday that there is always a Nash equilibrium, but sometimes the Nash equilibrium cannot be found in terms of the pure strategies. This is an example. The Nash equilibrium cannot be found in terms of hawk and dove, that are the pure strategies of the game, but in terms of a mixed strategy, that in this case is the one that is here.
Can I ask something?
Yes.
It's just a question about the payoff.
Yes.
Because originally you were writing the payoff with a comma, so it was like the payoff for 2 players.
Yes.
But then when you formalized it, it was like a matrix. My question is, like, are you focusing only on like a single player right now? Because
No, 2 players. Let's do this in. Okay, let's. The payoff matrix was like this. Okay, that this is hawk, dove, hawk, and dove. Okay, and now what I am saying, for example, in this case, let's go back. In the first case here, what I am doing is this. I have this vector, because this is the hawk vector, and here what I have is this vector. And this calculation is just multiplying this vector by this matrix and then by this vector. No, so what I'm having is one strategy here. One player is adopting this strategy, and the other player is adopting this strategy. So there are 2 players.
No, this I understand, but
yes.
I have a question. Like, it is like a step backwards.
Yes.
Because originally you were writing like a table, right?
Like
with
that?
a comma. Yeah, exactly.
Well, but that was only notation. The right thing to do is, if you are writing the payoff matrix, you should only write this value here. That is the value that will, it will be the payoff of the strategy in the file while competing with the strategy in the column.
Yeah, but this presupposes that it is like a symmetric game, I suppose, because like...
Yes, yeah, we are working with symmetric games, yes.
Mm-hmm. No, okay.
Yes.
Sure.
We're making that, like, if I think about 2-player games and
yes.
you're playing like a Nash equilibrium strategy.
Yes.
So you're making your opponent like indifferent of all the choices, the strategies that he can made. Like you don't know what he will play.
No, not indifferent. If you are playing the Nash equilibrium for you that are playing the Nash equilibrium, it is indifferent what the other individual will do. But for the other individual, it's not indifferent what he or she is going to do.
Yes, yes.
Okay, and so the right thing to do is also to play the Nash equilibrium, because if not, the payoff will be lower than that.
So if you play a game and
yes.
you don't know what the other player will do, so you will try to play the Nash equilibrium.
Yes, you don't know what the other player is going to do, but you assume that the other player is also rational. So the other player will have the same ideas that you have, if you are rational.
But we need this impose that the other player will think also this, because I'm saying if they play anything,
yes.
the expected value will be the same. No?
Yeah, but you have to assume that the other player is going to do the same, because, and this is done when you are saying that the other player is rational. And this is something that I told at the beginning. We are going to assume that the players are rational players.
Okay, okay.
So this is a very strong assumption.
Yes, yes, I remember that. But I'm thinking that, okay. I'm thinking that if you choose a Nash equilibrium, there is nothing that the other player can do, even if he doesn't think about what I'm going to do.
Okay.
He can play the worst strategy. I don't care. The
Yes.
expected value, it will be the
Yes.
same. So I don't care what the other player will do.
Yes. But it's not the same value.
Thanks. If you're playing the Nash equilibrium, no matter what the other player does, you're always going to be better than playing a other strategy. That's the idea. But you're not getting the same value, the same payoff. It's different. Yeah?
No.
I mean, so-
No matter what the other player does,
Yeah. That's
the
the
Nash equilibrium will be the best strategy against that strategy.
for you.
For you.
No.
For you.
For you.
Oh.
Yeah.
And as the other player is also rational, it will be the best strategy for the other player too.
Okay. Okay.
Okay, so finally, both of you will play the Nash equilibrium.
Okay.
Okay, I will show you something. Maybe it will be, it will an answer to your question. Let's see. Suppose that the population adopt a mis-strategy that is, this is a G, the Nash equilibrium. So suppose that there is another individual that enters with a strategy that is not the Nash equilibrium, okay? Suppose that it's a different strategy. So what I'm going to do is to calculate the payoff of this individual against an individual that is playing the Nash equilibrium. So I make all the calculations. I will not go into the details, but you can, and I will not go into the details because the letters here I'm using are wrong. So this should be a D, and this should be a G. So I mix my slides because I didn't want to show you that. But if you calculate the payoff of this strategy against the Nash equilibrium, what you will find is that finally the total payoff of any strategy with alpha here and 1 minus alpha here against the Nash equilibrium will get a payoff that is independent of alpha. So this is telling you that any other strategy against the payoff will get the same payoff, independently of the strategy. Okay? So this is something you can just make the calculations and you will see that the payoff of any strategy with alpha here instead of rho, while competing with a strategy with a rho here, will get the same payoff. Okay? So.
Vou falar em português.
Sim.
Acho que era mais ou menos isso mesmo que eu estava querendo perguntar, mas acho que eu me enrolei por causa do inglês.
Ok.
Então, para você que está jogando uma estratégia de equilíbrio de Nash,
Sim.
é indiferente o que o outro jogador vai fazer. Então,
Yes.
se você está num jogo e você não sabe o que o outro jogador vai fazer, o melhor que você pode fazer é jogar o equilíbrio de Nash.
Yes.
Independente, então, por exemplo,
Yes.
isso está muito relacionado com o jogo de pôquer. Eu gosto de pôquer, então eu estudei um cadinho bem supérfluo. Mas você vê muitos jogadores querendo jogar como se fosse um equilíbrio de Nash, que seria o que eles chamam de GTO, o melhor jogo baseado no interior de jogos. Só que a pergunta que sempre me ficou é, será que essa é a melhor estratégia, sabendo que seus outros jogadores são ruins?
The problem with poker is that you don't have the full information of the game because you don't know the cards of the other players. So in this case, you have full information. You know the payoff of each strategy, and you know which is the set of all possible strategies. When you are playing poker, you don't know the situation. You don't know in which state you are because you don't know what are the cards of the opponents. So you don't have full information. And when you don't have full information, all the things work more or less, but not precisely.
Entendi. Obrigado.
So that's the point with PUCA. So, and to go on with the idea, in the previous calculation, we showed that although the chosen strategy is in a set of the best answers, it is not the only one. Why? Remember that a Nash equilibrium was a strict Nash equilibrium if it was the best strategy to itself. And only this strategy was the best response to itself. In this, what we have been seeing in the previous slide is any strategy will be the best response to the Nash equilibrium because all of them will get the same payoff. So in this case, we have a Nash equilibrium, but this is not a strict Nash equilibrium. It's only a Nash equilibrium. But let's see another thing. Suppose that now I am going to calculate the other. Okay, I want to calculate. What we have done is calculating the payoff of, for example, alpha 1 minus alpha against rho 1 minus rho. Okay, but let's calculate a different thing. Let's calculate the payoff of rho 1 minus rho against alpha 1 minus alpha. Okay? And you will see that the payoff of this strategy against this one will be always higher than the payoff of this strategy against this one. Okay? So that's why even if any strategy will get the same payoff against the Nash equilibrium, when competing with another strategy, will get always the best payoff. And for that, we are going to do this calculation instead of this calculation. So we do the same. We calculate the payoff of this strategy. This is a G and this is a G. So this is rho and this is rho against alpha and 1 minus alpha. And when we do this calculation, what we get is that the payoff of this strategy, so this is the payoff of this strategy. We are going to do this, sorry. The payoff of this strategy against this one and the payoff of this strategy against itself, okay? And I am going to compare this payoff with this payoff. So what I am doing here is to calculate first the payoff of this situation here, and then the payoff of this situation here. And when I make these calculations, then what I do is, this is the payoff of this situation minus the payoff of this situation. This is the calculation here. And we can see that this subtraction is always positive, meaning that the payoff of the Nash equilibrium against any other strategy is always higher than the payoff of this same strategy while competing with itself. So the best thing to do is always to play the Nash equilibrium. So this completes the idea. Okay. So, yes.
Evolutionary stable strategy because the
Yes.
mutant against itself has a lower payoff than the mutant against the resident.
Exactly. This last calculation is telling us, as Rocio is mentioning, that the Nash equilibrium that we have found is also an evolutionary stable strategy, because the payoff of this strategy is higher than the payoff of any strategy against itself. So this completes the idea that the strategy that we have identified as a Nash equilibrium is not only a Nash equilibrium, but it's also an evolutionary stable strategy. Okay, yeah, that's right. So let's talk. We are moving now to evolutionary games, because up to now what we have is just a payoff matrix, and we know that we take a picture of a given situation. There is one player playing with a given strategy. There is another player playing with a different strategy. And we know by now that the best thing to do is to choose the Nash equilibrium. But suppose that at the beginning, the players don't know what to do, and they choose different strategies. How is that with time, the strategy of the whole population evolves towards the Nash equilibrium? How is the dynamics related to the game that can lead to the whole population to move, to change strategy, and to adopt the best possible strategy, that in this case is a Nash equilibrium? So for that, we need to add something else to the game. Up to now, we have the formulation of the game with the strategies and the payoff, but there is no dynamics here. So we need to think about dynamics, just to explain or to describe how the strategies evolve towards the best possible situation. And for that, we need to add something else to the game. And when we add a dynamics to the game, we are talking about evolutionary games, not games by itself, but evolutionary games. So the idea is that behaviors can be defined by trial and error. Adaptation and learning are key factors. Rational behavior constraints can be relaxed. Games are played in a population where each individual receives a score. So strategy that perform better, the idea is that strategy that perform better, that average spread while the others disappear. So if I am playing many times, suppose that we are not playing with rational players because they don't know or they cannot think, for example. And the only mechanism of going towards the Nash equilibrium is by the idea that a better strategy will survive and a strategy that is bad will just disappear because the payoff is just favoring the best strategy and is annihilating the worst strategies. So the idea is, how can we describe these possible dynamics for a given game? So we can think in a plethora of different dynamics, but there is a very strong condition. The idea is that the strong condition is the following. I will just describe what is written in the slide. Suppose that we are in a game with 3 different strategies. So what we have seen is that the strategies are located on this face. So the dynamics associated to a game cannot make me get out of this phase. Suppose that by a given dynamics, I am here and suddenly I am here. This is not allowed because this is not describing a correct strategy. So for a strategy to be a correct strategy, I should always remain within this simplex. If the strategy is making me to get out from that simplex, it is not a good strategy. So it's not that I can do whatever I want. I can propose different strategies or different dynamics, but the dynamics should always keep me inside this simplex. This can be represented formally in this way. Suppose that I call S the sum of all. Suppose that I have X, X1, X2, Xn, and this is a mixed strategy. We know that the addition or the sum of all xi should be equal to 1, okay? This is something that we have already defined. This is the condition to be within this simplex, okay? So I am going to call S to the sum of all these values. And suppose it is not 1. Suppose that it can take any value. And suppose that I propose a given dynamics, okay? And what I am doing is, I don't know the dynamics, but what I am trying to do is to calculate, or let's put it this. I want to calculate how this sum evolves in time. So this is equal to this. Okay? So what is important is that if S is equal to 1, then ds dt, when S is equal to 1, should be equal to 0. Okay? This is what I am telling, what I am saying, that 1 should be a fixed point of this dynamics. Okay? If S is equal to 1, then ds dt should be equal to 0. If this is something that I can give for sure, if this is something that is accomplished, so I am sure that these dynamics will not change or will not make me to get out from the simplex. Okay? But there is another thing. It is not enough with this to be equal to 0. Another thing that is important is that if xi is equal to 0, then should be equal to 0. Why that? Because if a strategy is not present from the beginning, I cannot create this strategy. So the idea, and it is important also because I don't want this value to adopt negative values. So if this is equal to 0, I need also this thing to be a fixed point for the whole dynamics. So I have two conditions. The first one is that if S is equal to 1, that is something true if I am choosing a right strategy. So for this strategy, 1 should be a fixed point of the dynamics. Okay? And the other situation is that suppose that I start with a given strategy, a given point here, for which one of the components of the vector x is equal to 0, so that component should remain equal to 0 along all the dynamics, along all the time. So there is no possibility to create a strategy. If the strategy is not present from the beginning, the strategy cannot appear. So this is something that is very strong and reduce the possibilities for dynamics I can propose to be dynamics for a game, for the evolutionary game. Yes.
The fact that xi the fact that xi equals to 0 implies that the xi dt is equal to 0. Could we argue that through evolution or through immigration, it could be greater, the derivative could be greater or equal to 0 in a more general case?
Okay, if you have a closed, suppose that we have a closed population like that.
A closed population?
Yes. So in this case, you cannot. From the beginning, we are avoiding the possibility of having different processes from those that are inherent to the game. So there is no immigration, there is no migration. The evolution of the strategies is only due to the dynamics of the game, and there are no external factors.
Okay, so if I like incorporate immigration, that would be like making it a dynamic game, something that I cannot change.
Yeah, you are changing. Yes, what you are doing by that is that the dynamics of the strategy of the population is not only dependent on of the game. It is dependent also on different processes such as migration. Okay. So suppose that I am talking about something that is related only to the game, and the only changes that can be produced in the population are due to the learning of which is the best strategy without adopting new individuals into the population. So I just want the population just to start to change the strategy profile in order to, for example, reach the Nash equilibrium. And doing that only by a process whose dynamics is only governed by what is happening with the game. Okay?
Okay, thank you.
So one of the most known, and this is not the only one, but one of the most known dynamics is the one that is called the replicator dynamics. And it's a dynamics that is right in the sense that these two conditions are fulfilled. And we will show that. Suppose that we call xi the frequency of the phenotype I. So suppose that we call xi as here the proportion of a given strategy in a mixed strategy. So suppose we have a mixed strategy, and this is the fraction of each of the strategies. So we have something like that. So the equation for the replicator dynamics is the following. It's the one that is there, but I prefer to write it down here to be more clear. What I am saying is that for each xi, the evolution of this xi would be proportional to xi and also proportional to the difference between the payoff of this strategy in the populations and the payoff and the mean payoff of the population. So this is the payoff of the population. Sorry, this is the payoff of I in the population minus the mean payoff of the population, and this is what I am saying. So this is payoff of I in population, and this is the mean payoff. So as you can see, F, the mean payoff, is defined as the sum over I of the fraction of I times the payoff of I in the population. So this is the mean payoff, okay? This is the one that is appearing here. So let's see if this is a good dynamics in the sense that these two conditions are fulfilled. So for the first one, this one is very clear. If xi is equal to 0, so the derivative of xi with respect to time will be always 0. Okay? If this is 0, this is 0. So there is no possibility to change the value of xi. So this condition is fulfilled. Okay? There is no problem with that.
How do you... posso fazer em português?
Sim.
Como você garante que essa equação ela é positiva? Essa média? Isso, como você garante que ela é não negativa?
Pode ser negativa.
Isso, como você garante isso?
It can be negative.
Ah, pode ser negativo?
Yes.
Ah, tá.
Yes. Yeah, it is strange that, yeah, it can be negative. Yes. This is, yeah, this should be greater than 0, okay? But the payoff can be negative.
Parece uma regressão. Eu estava pensando nisso parecendo uma regressão, como se fosse um ajuste à média, né?
Mm-hmm.
Então, até você deu o exemplo, né, da correlação não ser contrária,
Mm-hmm.
para poder a correlação ser certa.
No, but
Essa é
I
outra
mean,
coisa.
I'm not saying anything about the values of f here. And if all these values are negative, this will be negative. So this can be positive or negative or 0.
Okay.
So there is no problem with that. So what we can see is that if x is equal to 0 from the beginning, if xi is equal to 0, so this will be 0, and the derivative of xi with respect to time will be 0 all along the evolution. So this condition is fulfilled. Let's see if this one is also fulfilled by these dynamics. So Yes.
This equation, we are proposing this equation for the dynamics?
Yes.
Okay.
Yes. I am proposing this dynamics, or this equation, that is called the replicator equation. And what I am showing you is that this is a proper dynamics.
Nice.
Okay? So, because to be a proper dynamics, there were two things that should be fulfilled. The first one is okay. If this is equal to 0, so it will remain 0 along the evolution. The second one is to show you that ds dt is equal to 0 when s is equal to 1. Okay? So ds dt is equal to this. Okay? By definition, is equal to this. So this is equal to this. Okay? I'm just replacing this by the equation. Okay? So now I have this. And okay, yes. Yes, this. So this is equal to this. Okay? And if this is equal to 1, so this is equal to 0. Okay? So this works. If s is equal to 1, then this dynamics will just leave me within the simplex. If I start in the simplex, I will remain in the simplex. This is the important thing. There is no way I can get out from the simplex. Of course, if I start here, I can go to anywhere in the phase space, but this is not a correct departing strategy. A correct departing strategy is to be here. And if I am here, the s will be equal to 1. And if s is equal to 1, so I will remain within this simplex. Okay? So, as you mentioned before, this is a proposition. I propose this strategy, and I need to see whether this strategy is okay or not, if it is working or not. No, sorry, not strategy. I propose this dynamics, and I need to see whether this dynamics works or not. And it works. So I adopt this as a possible dynamics for my evolutionary game. This particular dynamics is called the replicator dynamics.
And maybe a question is,
yes,
why the name is replicator dynamics?
Do you know why?
I believe.
Please.
Because have you seen that if the payoff of I is larger than the mean payoff, so the population of I increase. Have you seen the derivative of xi over t is larger than one, so it's increased, but because it increases, the other strategy has to decrease. So they replicate the better fitness in some sense. That's I understand.
Yes, that's right. Those species with those strategies with the highest payoff will increase the fraction of the proportion, and those strategies with a payoff that is less than the mean payoff will decrease. Because if this is higher than the mean payoff, so the derivative will be positive. And if this is less than the mean payoff, so the derivative will be negative. So strategies with a payoff with the payoff that is higher than the mean value will increase. Strategies whose payoff is less than the mean value will disappear, will decrease. So that's the idea of the replicator. So, well, this is what I have been showing you, that 0 must be a fixed point, and 1 must be a fixed point. We have already shown these two things. So let's see, for example, how to apply this to hooks and doves. This is the payoff matrix, or this is the payoff for, okay. The fitness of payoff in this, we are just saying that fitness is equal to payoff. They are synonyms, okay? So the fitness or the payoff for the hook is, while competing with any mixed strategy, we don't know X. We don't know the value of X. X is just a variable. So the payoff of the species of the strategy hook against any other strategy can be calculated in this way. The payoff of the dove against any strategy can also be calculated in this way. Okay, so we will say that 1, 0 is the vector associated to a hook, and 0, 1 is the vector associated to the dove. Okay, so let's try to calculate the mean payoff. So the mean payoff is this one. So if just any value, any vector here with x and 1 minus x against x and y minus x. So this is the mean payoff of the population. The replicator equation for this, or for this, is we will have, in this case, an equation for x, for the hook, and we will have an equation for y minus x, for the dove. So in this case, this is redundant. There is no, it is useless to calculate the equation for this one, because it will be the same of the equation for this one minus 1. So we are only calculating this equation. We are applying the replicator dynamics only to the equation for the dove. And for the equation of the dove, the equation is this. Is equal to x, the payoff of the hook minus the mean payoff. Okay, this is the replicator equation for the hook, for the fraction of hook in a given population. So let's replace this by the payoff. We can just calculate this. The matrix is the usual matrix. This is the payoff of the hook, and the payoff, and the mean payoff is this. So we do this calculation, and finally we have, I am not going to make all the calculations, but believe me that after doing all this and replacing this here and this here, we finally got this equation. The equation for the, or the replicator equation for the payoff, for the hook is this one, okay? So let's try to analyze this equation from the point of view of a dynamical system, just to see which are the equilibrium of the system. Why we are doing that? Because if I am saying that I am interested in analyzing the evolution of the strategies of the whole system, I want to see if there is a stable state, and see whether, and also see if this steady state is stable or unstable. If I can find a steady state and this state is stable, so the whole dynamics will just drive me toward this state. So what I'm trying to do now is just to analyze this equation within the frame of a dynamical system, try to find which are the equilibria of this system, and analyze whether these equilibria are stable or unstable. And this is what I am going to do, okay? So what I'm trying to do is just to find the equilibrium of the system, and to find the equilibrium of the system, so what I have to propose is that the derivative of x with respect to time should be equal to 0. And when I propose this, if we look at the equation, what we can find is that x should be equal to 0, or x should be equal to 1. If x is 0, this is 0, so this is 0. If this is equal to 1, the whole thing is 0 because this turns to 0. And the other possibility is this is equal to 0. So x should be equal to g over c. This sounds familiar. This equilibrium is the Nash equilibrium we have already found previously. So let's try to analyze when these equilibria are stable or unstable. And this is something we're going to do in the next slide. Yes.
So you have 3 equilibrium points,
Yes.
but only one is a Nash equilibrium, right?
Well, that depends, yeah. That depends on the values of, I will show you, that depends on the values of G and C. I will show you that if G is less than C, the only Nash equilibrium is the one we know. If G is greater than C, so the situation is different. And I show you that if G was greater than C, Hawk was the Nash equilibrium. So I will try to see whether this is true or not, okay? So I will write down the equation. Okay. So suppose that G is greater than C. Okay? So I have 1, I have 0 here, I have G over C here. Okay? If G is less than C, so G over C will be in the middle, between 0 and 1. So let's see how I are the derivative. If I am between 0 and 1, this is positive because I am here between 0 and 1, so x is positive, so this is greater than 0. As x should be between 0 and 1, this will be also greater than 0. But if G is less than 1, so if x is here, if I am multiplying this by a value that is less than G over C, so the derivative in this situation will be also positive. Okay? If x is here, this value is also greater than 0. On the contrary, if I am in this situation, if x is greater than G over C, this will be always greater than 0, this will be always greater than 0, but now this term is less than 0. So the evolution is pointing in this direction. So if I am here, the derivative is just driving me towards G over C. If I am here, the dynamics is also driving me towards G over C. So in this case, we can say that this point is stable. Okay? So if G is less than C, there is only one, there are 3 equilibria, but only one of them is stable. Okay? And the only one that is stable is the Nash equilibrium. Now suppose that, let's move to a different situation. Suppose now that G is greater than C. So what we have now is that 0 is here, 1 is here, and G over C is here because G is greater than C. And again, let's try to analyze the derivative. This is always positive. This is, if I am between 0 and 1, this is also positive. And if I am here, if chi is greater than c, this will be always positive. So the derivative is just driving me towards 1. But if I am here between 1 and chi over c, this is positive, but this is negative. This is positive, so again, the whole thing is negative, and the dynamics is driving me towards 1. So in this case, this is always an equilibrium. This is an equilibrium, and this is an equilibrium, but the only stable equilibrium in this case is 1. So that means that playing Hawk is the Nash equilibrium. This is something that we already knew, but the idea is to show you how to use the dynamical system represented by the game plus the replicator dynamics to find the Nash equilibrium. Okay, yes.
Você disse agora que, nesse caso, então, todo mundo ser Hawk é equivalente ao equilíbrio de Nash.
Mhm.
Mas a gente só está olhando o ponto fixo da nossa equação dinâmica. Por que isso implica que é o equilíbrio de Nash? A pergunta pode ser feita assim. Para eu construir a minha equação dinâmica, eu só tive que satisfazer aquelas duas condições.
Mhm.
O que me garante que o ponto fixo da equação dinâmica é também um equilíbrio de Nash?
There is a theorem for that.
Okay.
Yes. So this is the next.
Sorry.
Okay, but no, it's okay. Thank you. There is okay. I am saying this very freely, but the truth is that there is a theorem that tells me exactly what you are asking. There is a theorem that tells me that any stable equilibrium of the replicator dynamics is a Nash equilibrium. And that's the answer for that. Okay? Yeah. So I will not just make the demonstration of the theorem, just mention it, but there is a theorem for that, so I can really say that without any problem that there is a close link between the steady equilibrium of a system whose dynamics is given by the replicator dynamics and the Nash equilibrium of any game. So they are very close related, they are the same. Let's show you another game. This is again stone, paper, and scissors. Remember, this was the payoff, or this is the payoff matrix, actually. And here we have, if I write the replicator equations, we'll have this shape. This is the replicator equation for scissor. This is a replicator equation for paper. And this is the equilibrium equation for rock. But again, if I am saying that x plus y plus z is equal to 1, so I don't need a differential equation for x, a differential equation for y, and a differential equation for z. I can write a differential equation for x, a differential equation for y, and then just say that z will be always 1 minus x minus y. So this equation here is redundant. I don't need this equation here. But when z is appearing here, I need to replace this value by this. Okay? So what I'm going to do is just to write these two equations, replacing this z here by this expression, by 1 minus x minus y. So I will write down these same equations, just not avoiding this equation and replacing the value of z when it's necessary. So these are the new equations. These are the same equations where I have just changed this value or this variable by this expression here. So these are the equations, the replicator equations for this game. And again, if I am just trying to analyze the the behavior of this system and the orbits of the system, the orbit should be on this face, on the simplex. The orbits cannot get out from the simplex. And when we analyze that, what we obtain is something like that. We obtain that the system has 4 equilibria, that these equilibria correspond to playing paper, this to rock, and then this to scissor or whatever, but these 3 equilibria correspond to playing a pure strategy. And there is a 4th equilibria that corresponds to playing 1/3, 1/3, 1/3. When we analyze this from the point of view of a dynamical system, we can find that these states are unstable, they are saddle points, and this state is a center. And the orbits on the simplex are like that. These are closed orbits that are always just changing strategy. Remember, when I showed you at the beginning what was happening with this game, just trying to find the Nash equilibria, what we finally did was just to make a sort of cycle moving all the time and without stopping at any of the equilibria. So in terms of pure strategies, there is no equilibria, or they are not stable equilibria. There is only one center that cannot be qualified as a steady point, as a stable point, but it's not unstable either. So this is, in this case, this is the Nash equilibria, but it is a center, so the orbits are around this point all the time. I can show you how to do that. These are the calculations. Just what I am doing is taking these 2 equations and making a linear stability analysis. And by doing this linear stability analysis, I can realize that this is the 0, 0, 1 is a saddle point. The 0, 1, 0 is also a saddle point. The 1, 0, 0 is a saddle point. And the 1/3, 1/3, 1/3, or 1/3, 1/3, 1/3 is a center. So I can do that, just analyze the system as a dynamical system, and I can find this. Okay? So I don't want to get into the details, but if you have questions, we can then just take a look at that. Okay? Because there is not too much time to get into the details. So, no, I will not show you this. So finally, what I am trying to show you is that by using the replicator dynamics, there is a possibility to make a classification of any game of 2 times 2. So I can take any game of 2 times 2 and just to characterize this game, and I can do this, and I will arrive to the conclusions that there are only 4 types of games. So if I take all the 2 times 2 games and I analyze them just by using the replicator dynamics, I will reach the conclusion that there are only 4 types of games. All the 2 times 2 games can be classified into these 4 different groups. Okay? So let's do that now. So each player can choose between 2 available strategies. Suppose that this is not the payoff matrix, but this is the payoff matrix. So I have strategy 1 and strategy 2, and again, 1 and 2, this is a symmetric game. And this is the payoff matrix for this game. And what I am trying to do is the following. Consider a population that plays this strategy E1 with the probability X and E2 with the probability 1 minus X. So for this population, the payoff would be this one, okay? Or the fitness would be this one. I am calculating this fitness by doing the usual procedure. That means X, Y minus X, with A, and here the rest of the population. So for this strategy, for that population, the fitness will be the same, will be this one. So the fitness of playing, so this is the mean payoff. Okay. I will write this in this way. This is the mean payoff. The payoff of the strategy E1 is this, the matrix and this here. And the payoff of the strategy 2 is this, the matrix and x, y minus x. Okay? So I have the payoff of strategy 1, the payoff of strategy 2, and the mean payoff. So what I am trying to do is just to write, again, if I have only two strategies, I can write the replicator equation not for the two of the strategies, but only for one of them, because one strategy will be with fraction x, and the other strategy will be with fraction y minus x. So it is not adding any information if I write the equation for both of them. So I will write the equation for only the first one, okay? So this is the calculation of the payoff of strategy 1, this is the payoff of strategy 2, and this is the mean payoff. What I'm doing here is this calculation, okay? So finally, when I write down the replicator equation for strategy 1, or for the fraction of strategy 1, what I have is this one. This is the expression, okay? Now remember this expression. I will write it down here because we will need to look at it again. So the payoff is x, y minus x, x plus b minus d. Okay, this is the payoff for x. Or this is, this is the replicator equation for x. So suppose that now I am doing a different thing. What I do is the following. I write a different matrix. From this one, I write a different matrix by subtracting in the first column the value in this file. So here I write A minus C. This is C minus C, so this is 0. And here I have B minus D, and here D minus B. So B minus B is equal to 0, C minus C is equal to 0, and here I have A minus C, and here D minus B. So I am just doing this. Why? I'm just trying to see what happens, okay? So instead of calculating the payoff for this game, I am trying to calculate the payoff for this game. This is a new game that has nothing to do with this one, okay? So what I'm going to do is just to write the mean payoff for this game and also the payoff for F1 and F2. When I write the replicator equation for x for this game, I get this expression. If I start to work with this expression, finally what I will get is this one. And if you can see that this expression here is the same as this expression here. So what I am telling is that the dynamics of this game is the same as the dynamics of this game. They are different games. They are not the same games. But the dynamics is exactly the same because the replicator equation is the same. Okay? So those are different games with similar dynamics. Not similar, with the same dynamics. Okay? So this is what I'm trying to exploit to, instead of using this payoff matrix with 4 parameters, to explore a game with only 2 parameters, because this is only one. I can replace I minus C by, I will do this, okay? I will have only 2 parameters, A1 and A2. And this is much simpler to analyze than this, where I had 4 parameters. So what I'm doing is that I'm not saying that this game is the same as this game. What I'm saying is that the dynamics of the former game is equal to the dynamics of this game. So by analyzing the dynamics of this game, I have also information about the dynamics of the other game. Okay?
Marcelo,
Yes.
mas, assim, qual é o limite, se eu posso falar isso, dessa modificação? Porque parece vamos dizer assim, uma decomposição da matriz. Mas essa modificação, até que ponto você pode modificar de modo que você mantenha o resultado? Assim, em termos de... você está diminuindo, você pode fazer multiplicar por um escalar, você pode fazer... Assim, tem algumas propriedades que você precisa seguir?
No, what I'm doing is, there is only one procedure. If I have, this is A, B, C, and D, for any value here. The only thing I am doing is just, this is something I can always do. And with that, I get this. Where so there are no constraints. I can always do that. Okay? Well, yeah. There are some things I can do. I need to show you, there are some properties on the replicator equations that tell you what can you do, and what you cannot do. I am using only one of these properties, and this property is this one, this one, that I am subtracting from this column a constant and from this column a constant. But there are some other properties, and sometimes you can also multiply by a scalar, or you can multiply by a scalar function. There are some other properties, but I am not exploring all of them. I'm just exploring this property, this operation. And what I have shown to you is that by doing this operation, the replicator equation for the original game is equal, or the replicator dynamics for the original game is equal to the replicator equation for this game. And this game and this game, this game, and this one are different games, but the dynamics is the same. And this is the property I am exploring. Okay? If there is an equilibrium here, there will be an equilibrium here, because the dynamics is exactly the same. So instead of exploring all the equilibria of this system, I am exploring the equilibria of this one, because it's much simpler to do that. Okay?
Relacionada à pergunta da Paula, ela pode pensar, por exemplo, que ela escreve a equação de replicadores para o problema original, e ali ela já observa que ela pode definir, agrupar parâmetros, não? E aí seria uma maneira dela... Estou chutando aqui.
Não. Tem algumas operações que você pode fazer na matriz e ela não afeta nada. É que, de fato, essa operação é uma operação totalmente reversível. Aí tem 4 ou 5 operações. Então, ele usou uma delas só, mas tem outras mais. Então...
Yeah.
Marcelo, you recently showed that the replicator dynamics is consistent with the hypothesis that you stay in the simplex, right?
Yes.
My question is, the replicator dynamics is the only one that is consistent? It's not the only one?
No, it's not the only one.
Okay.
No, it's not the only one. There are many of them. Yes.
Hay otras dinámicas también.
Yes. Maybe the replicator dynamics is the most famous because it has immediate interpretation in terms of biology. That is what Christian was mentioning before. The name replicator comes from a sort of biological interpretation, and the survival of the fittest is embedded in the replicator equation. But it's not the only one. Actually, the link between the equilibria of a given dynamics and the Nash equilibrium can be shown not only for the replicator equation, but for a huge family of different dynamics. This is only an example of this huge family for which you can actually verify the link between equilibria and Nash equilibria. Okay. So let's try to analyze now this game instead of the original game. Now, again, consider the population that plays E1 with probability X and E2 with probability 1 minus X. This is the payoff for strategy 1. This is the payoff for strategy 2. Now the expressions are much simpler than before because I have a 0 here and a 0 here. And this is the replicator equation for this game. Compare this expression here. There is something missing here. This expression here with this expression here. Here I have only 2 parameters, A1 and A2, and here I have 4 parameters. So from the point of view of the analysis I am trying to do, this is much simpler than this one. Okay. So this is the replicator equation for this game. And for this game, I can immediately see that there are 3 equilibria. The derivative of x with respect to time is equal to 0 if x is equal to 0, if x is equal to 1, or if this expression here is equal to 0. This expression here is equal to 0 when x is equal to A2 divided by A1 plus A2. So these are the 3 equilibria of the system. So what I am trying to show you is that there are only 4 possibilities. And that's why I have only 4 groups of games. All the games can be classified into these 4 possibilities. Okay? The possibilities that this equilibria being stable and these 2 being unstable, or this one being stable and this one unstable, or this one and this unstable. So there are many possibilities. There are 4 possibilities, and any game with the form of a 2 times 2 game will fall into one of these 4 possibilities I will show you in the next slides. Okay. Suppose that A1 is greater than 0 and A2 is less than 0. And again, remember that this is the equation for the evolution, and this is the equilibrium in the middle. If A1 is greater than 0 and A2 is less than 0, I have this. So what I'm saying is that this will not be here in the middle between 0 and 1. Will be in any other way. They are placed, but depending on the value of A1 and A2, this can be positive or negative, but will be here or will be here. Okay, but will never be here in the middle between 0 and 1. So if I analyze then the dynamics of this situation, taking into account that this point is not in the middle of 0 and 1, we can look that if I am in the middle between 0 and 1, if x is here, this is positive, this is also positive, and if A1 is greater than 0 and A2 is less than 0, this term here will be also positive, because this is positive, and there is a minus here, A2 is negative, so this expression is positive. So the derivative of x will be always positive. So for this situation, when A1 is greater than 0 and A2 is less than 0, the derivative between 0 and 1 is always positive. So if I am in the middle, I will be driven towards the 1. So in this case, 1 is the only steady state. 0 is not a steady state, and this point here is not a possible point because this value will not fall between 0 and 1. So in this case, when A1 is greater than 0 and A2 is less than 0, this equilibrium exists, but it's not an allowed strategy because the value here is not between 0 and 1. Okay? This is the opposite situation. Suppose that now A1 is less than 0 and A2 is greater than 0. So in this situation, again, this is positive, but this is negative, and this is also negative, and this point is not between 0 and 1, so the only possibility is that 0 is the steady equilibrium. So if this is positive and this is negative, the only equilibrium is 1, and if this is negative and this is positive, the only equilibrium is 0. Okay? Okay, well, this is something that I didn't mention. So suppose now that both A1 and A2 are greater than 0. So if A1 and A2 are greater than 0, now we can find a value of x1 dot that is in the middle between 0 and 1, okay, because both of them are positive, so A1 plus A2 is greater than A2, so this number is less than 1, but always positive. So in this case, this point will be here, but if we analyze the derivative, we can see that if I am between 0 and x star, the derivative is negative, because this is positive, but this term will be negative. So the derivative will drive me towards 0. On the contrary, if I am between x star and 1, this term is positive, and this term is also positive, so the derivative will drive me towards 1. So if both of them are positive, both 0 and 1 are steady states, and this equilibrium in the middle is an unstable equilibrium. Okay? And finally, we have the last situation when both of them are negative. A1 is negative and A2 is negative. And in this case, what we can see again is that x star is in the middle between 0 and 1, but contrary to what we have seen before, in this case, the derivative between 0 and x star is positive, so the dynamics drives me towards x star, and between x star and 1, the derivative is negative, so the dynamics is driving me toward x star. So those are the four cases that I can have. That I have only one steady state, only one stable equilibrium. That can be 0, that can be 1, or can be something in the middle. Or I can have two Nash equilibrium that can be either 0 or 1. Okay, so those are the four groups. And any game that is a 2 times time game will fall within one of these two groups. There are no other possibilities. Okay? So I will make a classification of the games. Games of the type 1 or 4, they are more or less the same, is when A1 is less than 0 and A2 is less than 0, or the opposite, when A1 is greater than 0 and A2 is less than 0. These are, so games of type 1 and 4 are more or less the same. Sometimes some people say that this is the same group. So the prisoner dilemma is an example of this game. Remember that the prisoner dilemma was something like I will call collaborate and defect. So collaborate, for example, got 1. Collaborate against defect got a 0. Defect against collaborate get 5. Let's call, and defect against effect was 0. So this is more or less the shape of the prisoner dilemma, and in this case we can see that, for example, if I write 0 and -4, and I write 0 and 1. So what I have here is one of them is positive and the other one is negative. So the prisoner dilemma falls within this group, okay? The Hawk and Dobbs falls within this type, the type 3, when A1 is negative and A2 is negative. Remember that in the Hawk and Dobbs, there was a Nash equilibrium, but was not 0 and 1, was something in the middle. So let's write the matrix, the payoff matrix for the Hawks and Dobbs. It was something like that. Chi minus C over 2, Chi 0, and Chi over 2. Okay, so there is a 0 here. This is negative, so I will write something here and something like that. So remember that C was greater than Chi, so this is negative. This is negative, so I am in a situation when both A1 and A2 are negative, so I am in this group. Okay? So Hawks and Dobbs is an example of games of this group. And then we have a different type of games. For example, this one that is called a coordination game. And this has to do with the question that you asked yesterday. Yes. A coordination game is a situation when you need to coordinate. For example, the war of sexes is a sort of coordination game. Remember that we have a mountain and beach, and mountain and beach. Okay, so the payoff. Suppose that I am writing the payoff for the woman. The payoff was 1, 0, 0, and 2. Okay, that was more or less the shape of the war of the sexes. And in this case, what we have is A1 is equal to 0, is greater than 0, and A2 is greater than 0. So in this case, we have two Nash equilibrium that are either going to the mountain or going to the beach. Okay? So those are the 4 types that I can find within these 2 times 2 games. Yes.
Wait. Hawk and Dobbs is coexistent, right?
Yes.
Coordination is by stability. You have to. You
Yes.
go, yes. And the other prisoner dilemma is invention, right? Or dominance.
Yes, dominance.
Ah,
yes,
okay.
dominance.
Thank you. I
Yes.
just want to.
Yes. Yes. Yeah, type 1 and type 4, there is dominance. Type 3, there is coexistence. Type 2, there is coexistence. And type 4, type 3, there is only 1. Yes. And there is no dominance, but there is a Nash equilibrium. Okay? Just to finish, I wanted to show you an example, a real example of lizards playing scissor, rock, and paper game. Okay? Yes. Okay. This is a species of lizard where the male may have 3 different colors in the head. For example, this is orange, this is blue, and this is yellow. Okay? And they behave differently according to the color. The males that, for example, the orange throated males, the males with orange color in the head, have more testosterone and they are aggressive. They defend large territories and they invade other territories, and mainly they invade the territories of the blue because the blue are not so aggressive. But in turn, the blue ones are less aggressive. They just live in smaller territories, but they know very well the females they have with him. So an orange male, the only thing that wants is just to get more territory, and as it gets a lot of territory, he cannot identify the females that are living with him or with it. On the contrary, the blues are not as aggressive. They have testosterone, but are not as aggressive. They tend to live in smaller territories, but they know exactly each of the females that are with him. And then we have the yellow one. And the yellow one is a weak male that is very furtive. It is important to say that the females are also yellow, so a yellow male can be confused with a yellow females because all the females are yellow. And the problem is the following. I will just pass the blackboard. The orange can defeat the blue by invading the territories, okay? But the yellow can defeat the orange also by invading the territories because the orange confuse the yellow males with yellow females because they don't know, the orange males don't know the females, so they don't know if a yellow male is a female or a male. So the yellow male that are furtives can get into the territories of the orange males because they are confused with females. But the blue males can defeat the yellow ones because they are more aggressive than the yellows, and as they know exactly each of the females that are living with them, when one of these yellow males tries to get into the territory of a blue, the blue says, "You are not a female, get out from here." Okay? So this strategy, so the yellow strategy is better than the orange strategy. The orange strategy is better than the blue strategy, and the blue strategy is better than the yellow strategy. So this is a rock, paper, and scissors game. Okay? So this is a representation of the game. So this is the yellow one that can defeat the blue one, but the blue one can defeat the yellow, and the yellow can defeat the orange. Okay? This is defensive, this is aggressive, and this is furtive. And when you see the evolution of these species in the nature, you find something like that, a cycle. So the amount, the fraction of each of the colors of the males is evolving in time like a cycle in the same way that evolved the rock, paper, and scissors game. So this is a real case of a rock, paper, and scissors game that occurs in nature. Okay, just wanted to show you this to finish with this part of the workshop. Okay, so well, that's all. We need to go to it. There were many things that I had to skip, and if there are some questions, we can just talk about now or later, as you wish. So that's all.
I have one question.
Yes.
So in this case, what you are telling us that you can explain coexistence without needing, for example, any kind of space information if they have like, I don't know, refuge or something like that. It's really only this kind of...
Yes, yeah, we can say that using a mean field model is okay for a colony of these lizards that do not take too much space to live within. So the home range of this lizard is rather small. So you are analyzing what is happening in a small fraction of the whole population. It's like an enclosed population, and you are only analyzing what is happening within this enclosure. Okay, so yeah, it's true that you have to take into account the space effects. But in this case, the home range is not so big, so you can just consider a mean field model, just neglecting the space.
Here they are analyzing the behavior. To say there is three kinds of behaviors.
Yes.
But you suppose that the environment is changing, for instance, all the species change the behavior as well. O sea, is to say they maintain the behavior, but they adapt to the new behavior in some sense.
No, but they change, the color also changes.
Oh, really?
Yes, yes. for example, in one generation, most of the descendant of the males will be blue, but then as most of them are blue, they are overcome or they are defeated by the oranges. So in the next generation, you have a higher proportion of oranges. So the yellow one can take advantage of the situation. So in the next generation, you will have yellow. Okay. So they are changing, really, they are changing the fraction of the phenotypes in the populations.
Posso
Yes.
falar? In this case, it's like it's important what other people are doing, the strategy and the frequency that the strategies. So maybe when one strategy is high, it's better for you to move another one. And in this case, is a best environment for that type of lizard.
Yes, just think in terms of rock, paper, and scissors, and you will
Yes,
understand
and they
this
were
perfectly.
very surprised to find this rock, scissor, paper in nature. Very, very surprised. But it's like almost all the time what you do, what you are going to do depends on what other people in the population are doing. That's Maynard Smith.
Yes.
To say that, sorry, if all the people are blue, probably for you it's going to be orange.
Yes.
Okay, because you are going, your fitness is going to be better. Mm-hmm.
Of the other's strategy. For example, I used to say that. En español, ¿verdad? Sí.
Well, but it's important here that there is no Nash equilibrium steady state, because if not, all the population will go towards the steady state.
Of course.
In this case, there is something that is a center, and a center is not a steady state.
Y eso pasa, por ejemplo, cuando tenés 3 estrategias, cooperadores, desertores y gente que sale de ese juego, ¿sí? Cuando tenés muchos cooperadores, vale la pena ser uno que no paga, un free rider, ¿sí? Porque vos no vas a apostar tu costo. Pero como eso es mejor, el pago de esa estrategia es mejor que el pago por medio, el Replicator Dynamics te llega a aumentar los free riders. Pero cuando hay muchos free riders, nadie pone plata, entonces ya no hay proyecto. Lo que te estaba diciendo ayer, que te estaba hablando, ya no hay proyecto. Entonces, ahí en realidad es mejor salir del sistema. ¿Sí? Entonces se va haciendo un ciclo. Pero cuando estás fuera del sistema, en realidad tu pago es menor a cuando estás dentro en un sistema bien organizado, como una sociedad. Entonces surge de nuevo. No sé si me estoy explicando bien.
Já discutiu, tá tudo bem.
O los impuestos de repente. Si todo el mundo no paga impuestos, es mucho más cómodo que pagar tu impuesto. O sea, el impuesto y el servicio, ¿verdad? Entonces yo prefiero no pagar mi impuesto. Pero si nadie paga impuestos, tampoco voy a tener servicio. Entonces paso de azul a amarillo, ¿verdad? Pero si es que en realidad no tengo servicio, es mejor irme a otro lado. Pero si estoy en otro lado, es mejor que vuelva aquí porque tengo el servicio y entonces entro de vuelta. Entonces comienza a hacer el círculo. Uh-huh.
Individualmente es mejor desertar, te conviene.
Sí, bueno, eso es
pero
el dilema del prisionero.
Sí, pero si todos hacen lo mismo, o en ese caso es mejor ser ¿cuál le domina a quién? Un blue que un yellow, pero después es mejor ser un yellow que un orange.
O sea que en este que están diciendo por ejemplo, en el caso de los impuestos, pagar, no pagar, que justamente son las 2 estrategias del juego, o sea, caería en alguno de estos 4 juegos, caeríamos en dilema de prisionero entonces, ¿no? Y en ese caso hay un steady state, que sería justamente el no pagar. Entonces, ¿qué te sacaría de ese lugar?
Okay, there are some examples where instead of playing a mean field game, you play a game with a spatial distribution. For example, if you play in a network, even if the not cooperating is the Nash equilibrium, you will go to the cooperation behavior. There is an emergence of the cooperative behavior that goes against the idea of the Nash equilibrium. But even if the players are rational, the players still, they are still being rational. If you have a network, the best thing to do sometimes is to cooperate. Because you are learning that if you don't cooperate, the things will be worse. So you look at there is a sort of cluster of cooperative people, and they are really doing much better than you, so you are moved to cooperate. So you need a sort of critical clustering of cooperating people to promote cooperation. But for that, you need some spatial distribution. If not, it is not possible.
At least Novak say that hay 5 razones que favorecen, 5 características que favorecen la cooperación.
Right.
Sería kinship, kin selection, reciprocidad directa, reciprocidad indirecta. Cuando tenés un network, ¿qué es lo que dice? Por eso uno ve en las simulaciones, ves clúster de cooperadores, es como que se agrupan. Y después sería group selection, que ese sí que es una cosa que algunos dicen que está bien, otro que es controversial group selection.
En conclusión, es mejor ser un desertor en clúster de cooperadores, básicamente. Eso es por un...
Funciona mejor que un grupo desertor.
Ah, ok. Eso.
Dentro de un grupo se conviene cooperar. Un grupo de cooperadores mejor que un grupo desertor.
Ok, ok.
I just think it's really interesting to think about some examples, like in real life / like social, like society, because like I am from insurance, so an insurance company, so like I see more on the corporate side, and so there's this thing called ESG, which is like environment, society, and governance, which is like some criteria for sustainable business and so on. It's kind of like, yeah, let's not get into that. Like, it's just controversial and not really effective. But there are some things like that they may just be like ignored. Because, for instance, like you can think about in Brazil, like all the mining companies that they allegedly are ESG and so on and so forth. Like it's a bunch of greenwashing, effectively. And so it is kind of like a dominated strategy if you think about it. If they like comply with ESG, if they don't do business in effectively like forbidden areas, like reserves, because if they don't do business in there, someone else will, and like will maybe even substitute them, right? So it is very tough, and like if we think about like game theory in a simplified way, like what guarantees that they abide to these rules is like laws, really, like because they become costs, really, and that's how businesses think about this. Like ESG is just a cost; it's not really a moral thing, or like really like we should say the environment. No, it's like costs, and if they don't comply, they have to pay taxes and so on. So like that's interesting to think about. Also, like the tragedy of the commons scenario, which like a scenario as well.
Yes. No, this is not what I... Okay, no, I just wanted to show you another example. Yes. Just, I will not talk about that, but just to mention you that there are many examples in nature of species playing a sort of game, or behaviors that could be explained in terms of game theory. Those are altruistic fish, but I will let this for questions or to talk later, okay? Because we need to go for lunch now. Okay?